Okay, this is Mr. Collier, and today we're looking at L'Hopital's rule. It's used for when we have limits of an indeterminate type, where we have, for example, 0 divided by 0 or infinity divided by infinity. And then we can't just plug in the numbers and we can't figure it out. We have to use a method like L'Hopital's rule. Okay, so here's L'Hopital's rule. If we have a ratio of two functions, then we can simply just find the limit of the ratio of their derivatives. This is what L'Hopital's rule tells us we can do. So let's look at some examples. First of all, you can only use L'Hopital's rule if it's the correct form. Notice the numerator, if we plug in 0, we get 0, and the denominator is 0. So we have the form 0 over 0, which means we can use L'Hopital's rule. So I'm going to use L'Hopital's rule, so it's going to be equal to, and I use this symbol to show that I just used L'Hopital's rule. So the derivative of 2tx is just 2tx times ln 2, and the derivative of x is just 1, so it's the same thing as this, as an x. And for this one, we don't have an indeterminate form, we don't have divided by 0 anymore, so we can just plug in x equals 0, and we have 2 to the power of 0 times ln 2. So the limit is just ln 2. Okay, the next one, we have again the form 0 over 0, so we can use L'Hopital's rule. And we have the limit as x tends to 0 of cosine x over 1. And we don't have divided by 0 anymore, so we just plug in 0. Cosine 0 is 1, so the limit is just 1. Next we have infinity over infinity, right? The numerator, the limit of the numerator is infinity, and the bottom is infinity. So we can use L'Hopital's rule because it's infinity over infinity. The limit as x tends to infinity of, and let's find the derivative. Derivative is 1 over x over 1. So as the limit as x tends to infinity of 1 over x is 0. So the limit of this is 0. And this one here, okay, we have the form infinity over infinity, so we can use L'Hopital's rule. And it's going to be limit as x tends to infinity of e to the x over n times x to the power of n minus 1. Okay, so we still have infinity over infinity. So what we could do next is we can use L'Hopital's rule again. So we have limit as x tends to infinity of e to the x over n times n minus 1, e to the n minus 2. Okay, so we still have infinity over infinity, so we can do it again. Actually, we do it many times. We do it, we use L'Hopital's rule n times in order to oops, that should be an x, in order to get this down to x to the power of 0, right? We use L'Hopital's rule n times, and the result will be the limit as x tends to infinity of n times n minus 1 times n minus 2 is going to be n factorial down here, right? Yeah, that's right. And this is going to be x to the power of 0, which is just 1, and the numerator is going to be still e to the x. And now we can see that this is going to be infinite, right? Because e to the power of x is the limit as x tends to infinity of that is infinity. So it's infinity, you can say it diverges. We have ln of cosine over ln of cosine. So, and first of all, let me explain this little plus sign. This means as x approaches 0 from the right. So we're not looking at negative numbers, we're looking at numbers like 0.1, 0.001. As it gets closer and closer to 0 from the right side of 0, what is this limit going to be? First, let's check to see if this is an indeterminate form. If you plug in 0, you get cosine 0 is 1. So you have ln 1 divided by ln 1 is 0 over 0. So it is an indeterminate form. And we can use L'Hopital's rule. So it's going to be equal to the limit, as in x tends to 0 from the right, of the derivative of that, which is 1 over cosine 3x times, we're using chain rule now, the derivative of cosine is negative sine 3x, derivative of 3x is 3. And similarly, the denominator is going to be sine 2x times negative sine 2x times 2. Okay, let's simplify that a bit. And I can take the 3 out of 2 and factor it out of the entire limit. And we have, we have sine 3x, the negatives we can cancel, sine 3x over cosine 3x, we can call that tan. So let's do that, tan 3x over tan 2x. Okay, now you plug in 0, tangent of 0 is also 0, so we can use L'Hopital's rule again. Okay, this is 3 over 2 times the limit as x tends to 0 from the right. Derivative of tangent is secant squared, so secant squared 3x times 3 over secant squared 2x times 2. Again, we can factor out this 3 over 2 and have 9 over 4 times the limit as x tends to 0 from the right of secant squared 3x over secant squared 2x. Now, do we have an indeterminate form? Secant is 1 over cosine. Cosine 0 is 1. So secant 0 is also 1. So we have 1 over 1. So this is just 9 over 4 times 1, which is 9 over 4. Okay. Next one. Now, next one, we don't even have a quotient, so we can rewrite it as a quotient. Okay, so this is like ln x over 1 over x. Okay, so this, see, ln x actually approaches negative infinity as it approaches 0 from the right, and 1 over x approaches positive infinity. But that's okay if it's both an infinity, so it works. So if we go back to our indeterminate forms, f of x could be positive or negative infinity, and g of x could be positive or negative infinity. So it is an indeterminate form. We can use L'Hopital's rule, and we have the limit as x tends to 0 from the right of 1 over x, and the derivative of this is negative 1 over x squared. So I'm going to simplify that a bit. I can multiply numerator and denominator by x squared, and it just turns out to be negative x, which you can just plug in 0, and it equals negative 1 times 0, which is 0. Okay, next one. We have this. Now this is 2 different fractions. You could split it up into 2 different limits, but that's not going to help you. What you can do is get a common denominator and add them together, and we can use L'Hopital's rule. So if we get a common denominator, we're going to have x minus sine x over x sine x, and the numerator, sine 0 is 0, so the numerator is 0, the bottom is 0, so this is indeterminate form, 0 over 0. So we can use L'Hopital's rule, and the derivative is going to be 1 minus cosine x. We'd use product rule on the denominator. We have sine x plus sine x plus x cosine x in the denominator. Oh, sorry, not. It's just sine x plus x cosine x. Sorry about that. Let's see if we still have an indeterminate form. Cosine 0 is 1, so 1 minus 1 is 0. Sine 0 is 0, and x cosine, yeah, that's going to be 0 as well. So we need to do L'Hopital's rule again. Limit as x tends to 0 of sine x over cosine x plus cosine x minus x sine x is the denominator. Now the numerator is 0 here, the denominator you're going to have 1 plus 1 minus 0, so we can actually do it. We can plug it in. We're going to have 0 over 1 plus 1 minus 0, which equals 0. Okay, and this next one, again, we don't have a fraction or a quotient, so you can rewrite secant and tangent as quotients. Okay, so you can rewrite secant as 1 over cosine squared x, and tangent as sine x over cosine x. And then we can get the common, not cosine squared, just cosine. Now we already have a common denominator, so that's the limit as x tends to pi over 2 from the left of 1 minus sine x over cosine x. Okay, and pi over 2 sine pi over 2 is 1, so we have 0 in the numerator, and cosine pi over 2 is 0, so we have the indeterminate form 0 over 0, so we can use L'Hopital's rule. No, it's not -1, it's just a negative sign up here. So the derivative of that is negative cosine x. The derivative of the denominator is negative sine x. Okay, so we have now pi over 2, we have 0 over 1, right? So we can actually plug it in, and this gives us 0. Okay, next one we have this, which doesn't look like a quotient, but it actually is. This is x over e to the x, right? And it's the indeterminate form infinity over infinity, so we can use L'Hopital's rule. And we have limit as x tends to infinity of 1 over e to the x. And now this is going to get infinitely large, so the limit is going to be 0. Now this one is interesting. We got the x up in the exponent. In this case, what you can do is you can write this as limit as x tends to infinity of e to the ln x to the power of 1 over x, right? So the e and the ln, they cancel, but because e is a continuous function, this means this is the same as e to the limit as x tends to infinity of ln x to the power of 1 over x. Okay, so we have e to the power of limit as x tends to infinity of 1 over x times ln x, which is like ln x over x. And this is the indeterminate form infinity over infinity. So we can use L'Hopital's rule. We have e to the power of the limit as x tends to infinity of 1 over x over 1. This tends to 0. So this is the same as e to the power of 0, which equals 1. Okay, this next one will be a little bit easier actually if we rewrite this as, get a common denominator and write this as x plus 1 over x to the power of 1 over x. So we can do our same trick as before and say this is equal to the limit as x tends to infinity of ln of this. Ln of that is ln x plus 1 over x all over x, right? And next I'm going to use our log rule to separate this. E to the limit as x tends to infinity of ln x plus 1 over x plus ln x over x. Okay, so we can separate that into two separate limits. Now, are they both indeterminate forms? Yeah, they both head to infinity over infinity. So we can use L'Hopital's rule, and we have e to the power of the limit as x tends to infinity. That is, the derivative of that is 1 over x plus 1. Derivative of x is 1. And then for this one, we're going to have 1 over x over 1. This heads to 0, and this one heads to 0, so we have e to the power of 0 plus 0, which is e to the power of 0, which is 1. Okay? And the next one, we can do the same trick again. E to the power of the limit as x tends to infinity of ln x to the power of 1 over x. Sorry, this is ln x to the power of 1 over x. So it's equal to e to the power of the limit as x tends to infinity of, this comes down, we have ln x over x, and this is also infinite, infinity over infinity. So we can use L'Hopital's rule. It is the same as e to the power of the limit as x tends to infinity of, now the derivative of this is 1 over ln x times chain rule times derivative of ln x is 1 over x, and the denominator is 1. Now we have this, when we have the denominator is 1, now these tend to infinity, so this whole limit tends to 0. So we have e to the power of 0, which equals 1 again.